Thank you for choosing to watch this video. This will be a brief introduction to the concept of analysis of variance, which is commonly known as ANOVA. For this example, I want to use the following context. A professor is teaching Physics 101, and there are 5 sections. There's about 21 students in each section. The smallest section happens to have 19 students. Students begin to raise the concern that the exam scores across the sections don't appear to be equivalent. And they're suggesting that the difference is due to the instructional quality in some of the sections. The professor is rightly concerned. She thinks to herself, this may be a problem. So what she does is she knows that there's 19 students in the smallest of the section, so she randomly takes 19 students from each of the 5 sections just to keep a balanced design, which is an issue which will come important later, but for now we'll just go with that. First, we need to think about the nature of the data before we progress. The professor takes the data and she puts it into 5 columns. This is referred to as parallel or by-group format. Some people call it the wide format. I prefer not to do that, but I understand the rationale. So each column represents data from a different group or a different section. And what's important to recognize is there's actually no connection across the rows. For example, in the first row, that row indicates 5 different individuals for each of the different sections. Alternatively, the data could be represented in serial or by subject format. And here you can see why it's called tall versus wide. So in this case, the groups are stacked one on top of the other, and a new variable is created to indicate the group membership. What you notice here is that each of the sections are listed 1, 2, 3, 4, 5. Only a few of the data points have been shown here to emphasize this. Now, it is the case that the row indicates the same individual. So if we're thinking about this from the perspective of the research question, the students claim that the exam score averages are different across the sections because the instructional quality is different. Well, it's actually not possible to test that causal element in this context, but the professor can test to see if there is any merit to the first claim, that is, if there are different averages across the different sections. Although she's not exactly convinced of this, she's willing to explore it further. Because we're using statistical inference, we need to convert the claim to a hypothesis. In this case, we'll have 2 hypotheses, the null and the alternative. The null hypothesis, which the professor is more inclined to believe, is that the average across the 5 groups are all the same. And the alternative hypothesis, which the students seem to be putting forward, is that at least one of the group means is different from the others. Upon reflection, you can see that these hypotheses are exhaustive and mutually exclusive. Either the first, the null hypothesis, is true, and if that's not true, then the alternative hypothesis must be true. In another video, I'll briefly show how to actually run the ANOVA using R and SPSS, but here I'll give the output from R, and we'll notice the table that's reported gives us an F value and a P value for the probability of observing that F value by chance alone. Other information is provided in this table, and we'll talk about that more at a later time. Here's the same value obtained using SPSS. Now the question is, how do we actually interpret these values of 3.029 or a significance level of 0.022? So I want you to imagine simulating the data with the same spread as our data. In the simulation, we take 95 scores, and with those 95 scores, we break them into 5 sections, completely by chance, completely at random. From there, we calculate a comparable F ratio for each of these simulations. Now, again, not going into much detail at this point, the F ratio is a measure of how spread out the group means are compared to what you might observe by chance. In the analysis that we ran, we obtained an F ratio of 3.029. In running 2,500 simulations, we actually found that the F ratio was at least 3.029 60 times, or 2.4% of the time. Here's a graph of those 2,500 simulations. So what this is emphasizing is how we can actually conceptualize the F ratio we obtained in relation to what we might observe by chance. So this actually says it is possible for the groups to all be completely equal, to come from a population where the averages across the 5 sections are essentially the same, because the 5 sections are drawn from people from the same population. Now there's always expected to be a little chance variation between the groups when you randomly draw and put 19 individuals in one group, 19 in another, and continue for 5 different sections. And based on that random chance, we would see an F ratio of 3.029, 2.4% of the time or larger. So we have to ask, is this a rare occurrence? And of course, this depends on our definition of what we consider rare, or in the statistical paradigm, on the chosen significance level. So a significance level of 0.02 and change would be considered unusual if we were using a significance level of 0.05, but not per se if we were using a significance level of 0.02. Next, we must make a decision about the null hypothesis. If it is rare, then we reject the null and in turn accept the claim of the group differences. Or we could accept that something unusual has happened by chance, but that kind of defeats the purpose of setting a cutoff for what we would consider rare. If it's not rare, then we fail to reject the null, and then there's essentially no support for the student's claim, no statistical support for the student's claim. So in this case, if, for example, the professor were using a significance level of 0.05, she might be inclined to explore the groups further to see if there actually is a difference between the groups. Thank you for listening.